So when we're talking about the study of motion and in particular forces, like a push or a pull on some object, first of all, just to clear up some misconceptions from the start, if you apply a force to an object, what happens to the object? If you just got an object and you push on it or pull on it, what's going to happen?
It might move.
It might move. If it's not already moving, it could start to move. But what if it is moving? If you've got some object in motion and you apply a force to it, what's going to happen?
It might move faster if it's the same direction or slow it down if it's the opposite.
Yeah, you might change the speed. You might, like if it's moving this way and you push on it that way, you're going to make it go faster. Or if it's moving this way and you push on it the opposite direction, you slow it down, maybe even bring it to a stop. Or alternatively, let's say it's moving this way and you apply a sideways force. What would that do to it?
Change its path.
Yeah, it's going to be moving on a different path now. So in general, a force doesn't really cause motion. If you got an object that's in motion already, then you don't need to apply any forces to keep it moving. It's just going to keep moving on its own. What a force does is change the velocity. Forces cause change in velocity. And one of the really important concepts to keep in mind throughout the study of motion is if there is no force acting on the object, what's it going to do?
Have no velocity.
Not necessarily. If you've got an object that's already in motion and no forces acting on it, what's going to happen?
Constant velocity.
Right, it has constant velocity. The velocity does not change because a change in velocity requires some force to be acting on the object. If there's no force, that means there's no change in velocity, but it doesn't mean there's no velocity at all. This is usually called Newton's first law. The force on an object is zero. Usually we say the net force, net in the sense of total. So the sum of all forces on the object. Then the velocity does not change. And this might mean there is no force acting on the object at all, or it might mean there are several forces, but they all cancel each other out and add up to zero. In general, if the total force acting on the object is zero, then the object's velocity does not change, which might mean it's at rest and staying at rest, or it might mean it's in motion and stays in motion with the same velocity. That is, not changing how fast it's going and not changing the direction it's traveling. So a straight line at constant speed. And this also goes the other direction. If the velocity does not change, then you know the net force on the object is zero. So it's really more of an if and only if statement. The if then works in both directions. On the other hand, if there is a force, or if there are forces that don't add up to zero, this gets into what we usually call Newton's second law, which is really just more of an extension of this. If there is a force acting on the object that causes the velocity to change, what do we call the rate at which velocity changes?
Is it acceleration?
Yeah, acceleration. Newton's second law is that force, or at least net force on the object, net in the sense of the total force acting on the object, so it's not really accurate to say force causes motion. Force causes a change in motion, and we call that rate of change acceleration, how fast the velocity is changing. And we can write that as a derivative. Acceleration is the derivative of velocity. And we can write that as an equation as well. The total force, the sum of the forces acting on the object, it should be proportional to acceleration. That is, if you want the object to accelerate at a certain rate, you'd apply a certain amount of force. If you wanted to accelerate, let's say 3 times as fast, 3 times as much acceleration, you would need to apply 3 times as much force. But what's the constant in proportionality here? What else determines how much force is required to make it accelerate at a certain rate?
Mass.
Yeah, the mass of the object plays a major role here. The more massive the object is, the more force is needed to make it accelerate at a certain rate. So if you have 2 objects that you want to both accelerate, you want to accelerate both of them at the same rate, but one of them's 10 times as massive, it's going to require 10 times as much total force to make that happen. Or alternatively, if you just apply the same force to both objects, the one that's 10 times as massive will still accelerate, but only at 1/10 the rate of the other one. And it's very useful here to think of mass as a difficulty level. We're usually accustomed to thinking of mass as like how heavy an object is or how much stuff is in the object. But in the sense of studying motion and forces, mass is all about difficulty of changing the motion. More massive means it takes more effort to get the same change in motion. Any questions on all that so far?
Can you just explain? I know you said that if the net force is 0, then velocity doesn't change.
Mhm.
Is that the same as saying that she said in her slides if motion doesn't change?
Yeah, in the
then-
sense of, because the velocity is describing the motion of the object in the sense of both how fast it's moving and also what direction.
Okay, so she said stationary or constant velocity,
Mhm.
and then she said like in a straight line.
Yeah, sorry, go ahead.
Oh no, I was just gonna say, what does that mean? Because I thought that if velocity was going in a straight line, then there would still be some kind of force acting on it.
Well, if you just have an object that's in motion and you're not doing anything to it, if there's no forces acting on it at all, it should just continue in a straight line with no change in speed forever. And this kind of seems counterintuitive because if you just like take a box and throw it, it's not going to keep moving forever. What's going to happen to it?
It'll stop.
Yeah, it'll eventually come to a stop. But that's actually because there is a hidden force acting on it. If you just got an object sliding on the ground, what force is acting on it and bringing it eventually to a stop?
Friction?
Yeah, friction is playing a role, which means that Newton's first law doesn't really apply. We don't have a situation where the net force is 0 because friction is acting on it and there's nothing balancing out friction. So we go to Newton's second law and say that the force of friction is causing acceleration, in the sense of the force of friction is causing the object's velocity to change, slowing it down and eventually bringing it to a stop. So Newton's first law, the idea of net force being 0, is very rare here on Earth, in the sense of it's very rare to see a situation where there's no forces acting on the object. You can certainly set up situations where the total force is 0. For instance, if there's a friction force making the object slow down, how could you balance that out so it doesn't slow down?
Push it?
Yeah, you can push it. If you're pushing the object to make sure it moves at constant speed in the same direction, then you are applying a force, but you're applying exactly enough force to balance out friction or whatever other forces. So the sum of the forces would be 0. So this is not saying if you're not applying a force, but maybe there are some other forces, then the object doesn't change velocity. This is saying if there's no force or if the total force is 0, then the object doesn't change velocity.
Okay, that makes a lot more sense. Thank you.
And that's true for both if there's truly no forces acting on the object, which we would really only observe if it's just floating out in space with no forces, not even gravity affecting it. Or if there are forces, but they all happen to add up to 0. In either of those cases, we would observe that the velocity does not change. And since velocity incorporates speed and direction of travel, how fast it's moving and which way it's traveling, constant velocity means it's not changing how fast it's traveling and it's not changing the direction of travel. It's just moving in a straight line forever. If the path curves, that counts as a change in velocity because you're changing the direction of travel. And since direction matters, what do we call a quantity where direction is important?
Vector.
Yeah, these are all vectors. Velocity being defined as the change in position, which we often refer to as r. So if r is position in the sense of like how far you are outwards from some reference point. So we can think of that as a radial distance. Like if you just got an XY coordinate system and we're talking about this location, we could think of that location as a position vector in terms of how far is it from the origin and in which direction. So that would be the position vector r. And you could think of this as like, if you wanted to describe precisely where you are, you could describe where you are in reference to some landmark. Like you could say, I'm currently 3 meters to the south of the big rock. or I'm 29 meters northeast of the flagpole, or something like that. You can describe your position relative to a landmark, but you need to describe how far you are from the landmark and in which direction. So position does count as a vector. Position, as described relative to some landmark or some origin of a coordinate system, incorporates how far you are from the origin and in which direction. So position does count as a vector. And the derivative of a vector is also a vector. So velocity could be thought of as how far you're traveling, including which direction you're traveling in, divided by how much time it takes you. Meanwhile, how do we define acceleration? That was derivative of velocity, right? Acceleration is derivative of velocity, that is how fast the velocity is changing. But velocity itself is a vector, it incorporates direction, which means acceleration also includes direction. It's telling you how much the velocity is changing as time passes, including which direction the change is in. And since acceleration is a vector, also is mass a vector or not? Does mass have direction? No, it's just a scalar. A scalar in the sense of it's rescaling the vector by multiplying it by some number. Because you wouldn't really say an object has a mass of 5 kilograms to the southeast. It's just 5 kilograms. So mass is a scalar, acceleration is a vector, multiply a scalar times a vector, and the result is another vector. Like if the mass is 3 kilograms, the force is going to have a numerical value that's 3 times as much as the numerical value of the acceleration. And it keeps the same direction. So the total force has to be in the same direction as the acceleration. Any questions on that so far? Also, in terms of the units of measurement, because anytime we introduce some new quantities, it's a good idea to look into the units there. Starting from the beginning, what is position measured in? If you want to describe where you are relative to some starting point. Yeah, that's going to be in meters. Position vector is a distance. It's also sometimes called a displacement vector in terms of how far displaced are you from the origin of the coordinate system. And then dt, time, would be measured in what? Yeah, time is measured in seconds, so velocity is going to be measured in meters per second. So velocity is measured in meters per second. And the usual terminology there is velocity is a vector. Velocity includes how fast you're going and which direction you're traveling in. If we say speed, we usually mean how fast you're traveling, but we don't care about direction. So we would describe that as speed is the magnitude of velocity. Magnitude meaning essentially absolute value for vectors. How big it is, but not caring about direction. Plugging that into the definition for acceleration, we know velocity is measured in meters per second. Time, again, is measured in seconds. So if we divide those, what do we get? What's going to happen? Yeah, that's going to be meters per second squared. Since the seconds in the denominator and more seconds in the denominator combine to seconds times seconds. So acceleration is measured in meters per second squared, sometimes also read out loud as meters per second, in the sense of how many meters per second your velocity changes by every second of time that passes. For example, if the acceleration is 15 meters per second squared, that means every second your velocity changes by 50 meters per second. And if we fill that into the equation relating that to force, we've got acceleration measured in meters per second squared, mass measured in kilograms. If we multiply those together, we get kilogram meters per second squared. And what do we call that? What are the usual units of measurement for force? Yeah, force is measured in newtons. And newtons is just an abbreviation for kilogram meters per second squared. So that's what we mean by newtons. Newtons is just an abbreviation for kilogram meters per second squared, because it gets tedious to write out kilogram meters per second squared over and over again. Any other questions on that so far? So to recap, if you don't apply any, if there's no forces applied to the object, or if there are forces, but they all add up to 0, then the object's velocity does not change. It just keeps moving at the same speed in the same direction, straight line forever. The only way you can make the velocity change is if the forces don't add up to 0, in which case the total force on the object would be mass times how fast it's accelerating. Momentum, if the net force is 0, that doesn't mean momentum is 0, it means there's no change in momentum. Because if we want to introduce the idea of momentum here, which is essentially another perspective on the same thing. Let's look into how momentum relates to this. Momentum, usually written as a lowercase p. How do we define the momentum of the object?
Mass times velocity.
Yeah, momentum is mass times velocity. Velocity is a vector, mass is a scalar. It just changes the size, but not the direction. So momentum is also a vector that's pointing in the same direction as velocity. It's just been rescaled by the mass of the object. So momentum takes both of those quantities into account. Momentum is a description of the motion of the object, including direction of travel, and the mass. And since mass represents how difficult it is to change the velocity, momentum is really a description of its motion combined with how difficult it is to change that motion. I think that's probably one of the best ways of thinking of momentum. It's a description of the motion of the object and incorporating how difficult it is to change that motion. And if we take a look at the units of measurement, we've got the usual meters per second for velocity. We've got kilograms again for mass. So momentum is going to be just those combined, kilogram meters per second. And that doesn't really have an abbreviation as far as I know. It's just written out as kilogram meters per second. But that's what the units of measurement would generally be for momentum. And if we combine this with the idea of Newton's first law and Newton's second law, Newton's first law is the net force is 0, velocity doesn't change. And what does that tell you about momentum? Also doesn't change. So this is another way of describing Newton's first law. You could also describe it as if the net force is 0, then the momentum of the object does not change. So you can rephrase the Newton's first law and Newton's second law in terms of velocity or in terms of momentum. If we want to apply Newton's second law, momentum is all about velocity, but force is really about the derivative of velocity. So one other thing we could do here is we could apply a derivative to both sides. Take the derivative of both sides with respect to time. On the left side, we get the derivative of momentum. That is how fast momentum is changing. On the right side, what do you know about mass? Is the mass going to be changing at some rate?
No.
Yeah, mass should presumably be a constant. So if you have a constant multiplier, what can you do with a constant multiplier in a derivative?
Take it out.
Yeah, that constant multiplier can be pulled out, so we get mass times derivative of the thing that is changing. But what do we call the derivative of velocity?
Acceleration.
Right, so we can rewrite mass times derivative of velocity as mass times acceleration. And we know from Newton's second law that mass times acceleration is the net force on the object, the total of all the forces acting on the object. So another way of phrasing Newton's second law, instead of describing it as this total force on the object equals mass times acceleration, you could write it as the total force on the object equals the derivative of momentum. That is how fast momentum is changing. So again, you can think of both of these in terms of velocity and acceleration, or in terms of momentum and the derivative of momentum. That net force being 0 means that the velocity and therefore the momentum do not change. If there is a net force, then the net force equals mass times acceleration, or derivative of momentum, which is just another way of writing the same quantity. So the total force tells you how fast the momentum is changing. And if the total force is 0, then the momentum doesn't change. It just keeps moving with the same momentum, that is same speed and same direction, which could be 0. Maybe it's already staying still and it continues to stay still. Or maybe it's already moving and it continues to move in the same fashion, the same direction, straight line. Note that moving in a circular path doesn't count as continuing the same sort of motion, because a circular path is changing direction all the time. So circular motion, any motion along a curved path, does count as acceleration and requires a force, even if the object is continuing with the same speed, because direction matters here. Any other questions on these terms so far? What 4 forces do you mean?
Like gravity, normal, friction, and something else. There was one other one.
Like an applied force or a thrust force or something?
Yeah, we started going over it in lecture. Oh yeah, it was the push, normal, friction, and gravity.
Okay. I want to emphasize first that those are just one example of some forces that could be acting on an object. There are a lot more kinds of forces than those. But those are forces that are often relevant in certain situations. But yeah, let's try out an example here. Let's say we have an object that is on the ground and we're just applying, let's say we're not touching it at all. If it's just on the ground here, what forces would you expect to be acting on this object?
Gravity.
Yeah, we're definitely going to have gravity because presumably this object has mass. In fact, let's say we know what the mass is. Let's say the mass is 6 kilograms. And presumably this is an object with mass that's on or near a planet. So that means the force of gravity from that planet is pulling it, and pulling it in which direction?
Down.
Yeah. And typically when we're dealing with forces, it's often useful to treat the object as just a single point in what we call a force diagram or a free body diagram. So if we just draw this object as if it were a single point, and we can draw all the forces as arrows emanating from that point. We know gravity is acting on it straight down. So force of gravity. And how would we calculate how strong that force is?
Mass times gravitational constant. 10.
And keep in mind, when we say constant, this is not really necessarily a constant. It's going to be the same if you're on the same planet and the same elevation the whole time. But if you get further away or closer to the planet, G does change. Or if you go to a different planet or moon, G is going to be very different. So this is the G value specific to the planet you're on and the altitude you're at. But yeah, on Earth and on or near the surface, it's going to be 9.8 meters per second squared. Or if you just want a rough mental estimate without needing a calculator, it's approximately 10. But generally, if you're going to be using a calculator anyway, I would just use 9.8 or 9.81 if you want to be really accurate. 10 would be if you just need a quick mental estimate and don't want to take the trouble to take the time to go through the exact calculation. So that's G, and then M is the mass of the object. So in this case, we've got 6 times 9.8. Or let me include the units there. 6 kilograms times 9.8 meters per second squared. So 6 times 9.8 is going to be 60 minus a fifth of 6. 60 minus 1.2, so 58.8, I believe. And then kilogram meters per second squared would be newtons. So that would be the force of gravity on the object. That's how strong gravity is pulling it down. also known as the weight of the object. Weight, by the way, does not mean the same thing as mass. Weight would refer to how much the force of gravity is pulling on the object. And you could think of G, since G is measured in meters per second squared, what kind of quantity is G?
Acceleration.
Yeah, G is an acceleration. Specifically, G is the acceleration of an object that's just in free fall. If you just take this object and drop it on or near Earth, then it's going to accelerate downwards. It's not just falling at a constant speed, it's falling and getting faster and faster at a rate of 9.8 meters per second. So G represents how fast it would be accelerating if it were in free fall. But this object is not in free fall, it's just staying put on the ground, because what other force is acting on it? Sorry, what was that?
Normal.
Yeah, a normal force. And normal isn't really a kind of force. Normal is really a direction. Normal is just a mathematical term meaning perpendicular. So specifically the normal or perpendicular force from what? What other object is pushing it to hold it up?
Would it be the
The
ground?
table.
Yeah, the ground itself or the tabletop, whatever surface it's resting on. So the ground or the tabletop is applying an upward force. Upward because that's perpendicular to the surface. Normal literally just means perpendicular to some surface.
So if the ground was slanted, would
Mhm.
the normal force be perpendicular to that, or would it still be like straight up?
Always perpendicular to the surface. Normal by definition means perpendicular to some surface. So if you've got some surface, no matter what orientation the surface is in. So if you had some object that was on a slanted line like this, the normal force is always perpendicular to the surface itself. So that would be this way. No matter what orientation the surface is, normal means perpendicular, and specifically perpendicular outwards from the surface. And of course, there might be other forces as well, but normal force is always perpendicular by definition. In this case, though, if the tabletop is just level, the normal force will be straight up. And keep in mind that forces are always between pairs of objects. You can't just have a force out of nowhere. Like the normal force is the force on the box from the tabletop or the ground. What's the force of gravity from? What object is using gravity to pull the box downwards?
The Earth?
Yeah, the Earth itself or whatever planet this is on. So anytime you're talking about a force, you should be able to identify the two objects that it's interacting between. That this force is the Earth pulling the box down. This force is the surface pushing the box up. And that goes back to another law we call Newton's third law. It's often phrased as for every action, there is an equal and opposite reaction. But I find that often that wording often tends to just confuse things further. I just think of it as forces come in pairs. Forces come in pairs and represent interactions between two objects. And specifically, if the Earth is pulling the box down with a force of 59 newtons, what else is happening? The Earth is pulling the box down and also
Do you mean like the box is doing an opposite force or something?
yeah, specifically the box is applying an opposite force to the Earth itself. You can't have just one object experiencing a force in isolation. It's two objects applying forces to each other. So if the Earth is pulling the box down, the Earth is pulling down on the box with a force of 59 newtons. The box is also pulling the Earth up. What's really happening here is the two objects, the Earth and the box, are attracting each other. So the box is feeling a downwards force from the Earth, and at the same time, the Earth is feeling an upwards force from the box with the same strength, same magnitude, but opposite direction. So the box is feeling a downward pull of gravity from the Earth with strength 59 newtons. Meanwhile, the Earth is feeling an upwards pull of gravity from the box with a force of 59 newtons as well. Those are the equal and opposite forces that Newton's third law is talking about. And we can phrase this as an equation by saying the force from object A on object B is the exact opposite of the force from object B on object A. Force from A on B equals the opposite of force from B on A. Opposite in the sense that they're the same magnitude, but exact opposite directions. Like the Earth pulling the box down and the box pulling the Earth up. And it's often described as two forces, but I usually just think of it as the same force, the same interaction viewed from two different perspectives. That there is a 58.8 Newton interaction between the box and the Earth. The box feels it as a downwards force from the Earth feels it as an upwards force from the box. Any questions on that so far?
Sorry, this is going back to the one in lecture because I was kind of confused, but on the one that's slanted, the normal force is perpendicular to the surface. But then she drew an upward force called surface, like force of the surface, which is always perpendicular, or not perpendicular, parallel with gravity. Is that so? Is there still a force of surface coming straight up on the slanted one?
Well, the normal force is the force from the surface, or at least it's part of the force from the surface. Yeah, there might also be a friction force. The surface can provide a normal force, which is perpendicular to the surface by definition, and can also provide a friction force, which is along the surface itself.
Okay, because she has the force of gravity down, the force of surface up, the force of friction to the left, and then the force of the normal perpendicular to
the surface force being described there might just be the friction force and the normal force combined. Because the normal force is only part of the force exerted by the surface. The friction force is the other part. So you could combine those and just say the total force from the surface on the box. But it's usually more convenient to split it up into two forces.
So she was just adding them together.
Right.
Okay.
Because if you have, going back, let me draw a free body diagram for this as well. For the box on the slanted surface, we still have gravity pointing straight down as it always does. So we still have force of gravity pointing straight down. In this case, the normal force is going to be on this diagonal because it's by definition perpendicular to the surface. But there could also be a friction force, or there might not be. It's possible that this is a frictionless surface and that there is no friction force. If there is no friction force, do these forces add up to zero?
No.
Which means if the forces don't add up to zero, what's going to happen to the object?
It's going to
move.
Yeah, or maybe it's already in motion, but it's going to
Speed up, accelerate.
speed up. Or if it's on its way up, maybe you give it a push and it starts sliding up, it's going to slow down, then stop and change direction. Always keep in mind, forces do not cause motion. Forces cause change in motion. Forces cause acceleration to happen. So the fact that these forces do not add up to zero means that the object is going to accelerate. It's going to change its momentum. And how can you tell from this diagram that these forces do not add up to zero? Or how would you add those forces together geometrically?
would it be
You would add their X and Y components?
Yeah, well, there's a couple of ways you could do this. One way is you could split it up into X and Y components. Like let's say we keep gravity as just a Y component and that's it. Normal force, we could split up into an X component and a Y component. So it might be possible that the upwards and downwards components, upwards from normal force and downwards from gravity, it's possible maybe those cancel out, but there's nothing to cancel out the X component. So that means there would be an uncanceled X component and the object would accelerate. Or you could also draw this out geometrically, set up any coordinate system you like. And from the origin, we could say, let's say we're adding together force of gravity plus the normal force. From the origin, force of gravity is straight down. And then from that as our new starting point, we could add the normal force. that doesn't bring us back to our starting point. So that means there is a non-zero total force. The total force would be from the original starting point to the end of the last vector. So this would be the net force here. A straight line vector from the beginning of the first vector to the end of the last vector. So that's often a useful way to geometrically or visually add vectors together. No matter what kind of vectors they are, if it makes sense to add the vectors together, you can draw that by drawing one vector from the origin to some new location. Yeah, exactly. We usually call this the head to tail method. And then from that as your new starting point, follow the next vector to get to some other location. Or if you were adding several more vectors together, you would just start from there, add the next vector and the next and the next. No matter how many vectors you're adding together, the result, the total, is going to be a straight line vector from the origin, beginning of the first vector, to the end of the last vector you're adding. And I usually think of this as like following a set of directions for motion. Even though these are describing forces, not displacement, you could think of it as like this vector says go so many miles to the south, and then this one says go so many miles to the northeast. The total displacement from the origin, from where you started, is this far in this direction. So the total, if you think of each of these vectors as directions to go some distance in some angle, the total, the net of these vectors is just these straight line directions from the starting point to where you end up.
On that graph, because you were talking about displacement, but isn't velocity the derivative of displacement?
Yes.
So then how,
Mhm.
oh, no, I was just gonna say, so then how are both of those, because in DL, we were first using the arrows as displacement, and then we started calling them velocity. And so I was a little confused on how we were able to exchange those terms.
They're not interchangeable. They do mean different things. So that these force vectors definitely do not represent displacement. This normal force doesn't mean go some distance in this direction. This isn't a distance at all. It's how strong the force is and in which direction. But even though these vectors, and in fact, most vectors do not represent distances, the mathematics of adding vectors together works the same no matter what the vectors represent. So regardless of whether the vectors are distances measured in meters, or forces measured in newtons, or accelerations measured in meters per second squared, no matter what the vectors actually represent, you can still add them in the same way you would add together position vectors, as long as they're all measuring the same thing. So even though they're not position vectors, they're not truly displacements in meters, you can visualize it as if they were displacement when you're adding or subtracting them. Any other questions on that so far? Then let's try some actual calculations here. Going back to the simpler example first, if it's just on flat level ground, you've got a downwards force of gravity that's 58.8 newtons straight down. What does that tell you about the normal force from the surface?
Has to be 58 in the other direction.
Yeah, that's going to be another 58.8 newtons in the opposite direction. And how do we know that? If we needed to explain that, how would we justify our knowledge that this is also 58.8 newtons?
There's no net force, so the x components or the y components have to add to 0.
Yeah, we know this object, specifically that we know this object is not accelerating. There's no change in velocity in the sense that its starting velocity is 0 and it continues to be 0. No change in velocity means that the forces have to add up to 0. So if you've got 58.8 newtons downwards and only one other force, that other force has to be 58.8 newtons upwards to balance that out. So they add up to 0.
So you said that,
sorry, go ahead.
oh no, so you said that if there's no velocity change, then that means there's no net force. Is
Right.
that always going to be the case?
Yes, that is exactly what Newton's first law is saying. There's 0 change in velocity if and only if there's 0 total force.
Okay, thank you.
And the only way to get the velocity to change, or to put it another way, to get the momentum to change, is to have the total force on the object be non-zero, in which case the total force on the object is going to equal mass times acceleration, which can also be written as the rate of change, the derivative of momentum. And this equation alone also implies the first law. You don't really need the first law separately. The second law implies it, because if the net force is zero, then you know the acceleration is zero, and the derivative of momentum is zero. In other words, momentum is constant. So the first law is implied by the second law as well. You don't separately need the first law. It's just listed separately traditionally. Let's see if we can apply the same idea to the object on the surface as well. If we have the object and we've got the force of gravity, let's say it's the same 6 kilogram object, so we have the same 58.8 newtons. Downwards. And we've also got a normal force whose strength we don't know yet. And also a force of friction. Let's assume for the moment that this is not accelerating at all. Let's say it's just either sliding at a constant rate, or maybe it's just staying still. In fact, for simplicity, let's assume it's just staying still. That means the forces have to add up to zero. What other force could be present to balance out the fact that these don't add up to zero?
Resistance or friction?
Resistance in what sense? From what other, what force?
Like the horizontal force from the surface.
It's not strictly going to be horizontal here. It's actually going to be parallel to the surface itself. And what do we usually call that force? The force of an object sliding, or a force preventing it from sliding.
Friction?
Yeah, this is friction. Since the object is not sliding, we would call this static friction. If it was in the process of sliding, we'd call it kinetic friction, which can have a different value from static friction. Usually kinetic friction is weaker than static friction, because it can be difficult to get an object moving in the first place, but once it is moving, it's fairly easy to keep it moving. Kinetic friction tends to be weaker than static friction. So the friction force is going to be parallel to the surface and in the direction that tries to prevent the object from moving. So this would be the force of friction. And we also don't know how strong that one is. But we do know these forces all have to add up to zero. And if they all have to add up to zero, we can set that up as an equation. Though if you're going to be doing actual calculations with vectors, usually it's better to split them up into components. Because working out the trigonometry of, like, let's say you've got this vector plus the normal vector plus the force of friction. Figuring out how these add up to a complete triangle so that they balance out to zero, that is, returning to the starting point. The trigonometry there can be pretty involved, pretty difficult, especially if it's not a right triangle. This one does happen to be a right triangle, but it could still be annoying to analyze. So usually what we do instead is split this up into components. And usually we use X component horizontal and a Y component vertical. But in this case, because two of the vectors are already on this nice, neat other coordinate system, it often makes sense to use a different coordinate system. Let's say we take this parallel axis, parallel to the surface, and call that our new x-axis, and another direction perpendicular to the surface and call that our new y-axis. That way, the normal force is already entirely in the y direction, and the friction force is entirely in the x direction. So the only thing we would need to split up is the gravity force. Specifically, we need to find a x component of gravity and a y component of gravity. That makes a right angle. So if you have a single one other angle here, if we know the force of gravity is 58.8 newtons, that's the hypotenuse. If we know some other angle, like let's say we know the angle that the ramp makes with vertical. If you know that angle, then you can find the other sides using trigonometry. And then the x component has to be balanced out by the friction force, and the y component has to be balanced out by the normal force.
Oh, so whatever we get using the theta from gravity, then we know that the x is just the friction, and then the y is the normal.
Right, because in this case, we know they have to add up to 0. So whatever the gravity's y component and the normal force have to be exact opposites. And gravity's x component and the friction force have to be exact opposites. The big advantage of splitting it up into components is that the components don't interact with each other. The x components can be treated on their own in one separate equation, and the y components can also be treated on their own in a separate equation. So you can make separate equations that only involve those components, and then solve that equation or system of equations to find the unknown variable or variables. Any other questions on that?
No, that makes a lot of sense. Thank you. So we can get the x and the y just from the theta.
Yes, thanks to right triangle trigonometry. Because if we have this triangle, and we know this is a right angle, and we know this side is 58.8, and let's say we know this angle, you can use sine and the 58.8 to find the opposite side, and you can use cosine of the angle and the hypotenuse to find the adjacent side.
Oh, I didn't realize we could use the 58.8. Okay, that makes sense.
Yeah, if you know the hypotenuse, that is how strong the vector is, the magnitude of the vector, and the angle, you can use right triangle trigonometry to split it up into x and y components. And if you need some
Okay,
extra practice with that, I've got a couple of worksheets on. If you go to math.andsheets.org and click on Physics 7 Math Review, there's a list of worksheets with math review stuff. The last two are on trigonometry review and vector arithmetic. So you might find those useful to get some practice with this stuff.
Okay, thank you so much for your help.
You're welcome. See you next time.